Hello, for today's video lecture, we're going to be talking about orientation, angular displacement, angular velocity, and angular acceleration. So in engineering mechanics, the concepts of orientation, angular displacement, angular velocity, and angular acceleration supplement the concepts of position, displacement, velocity, and acceleration to fully describe the motion of rigid extended bodies. So these are necessary because rigid bodies can both translate and rotate during motion. If I've got some bar and it's moving from time 1 to time 2, I not only need to describe the change in position, but also the rotation that happens between these 2 points. So starting off with orientation. The concept of orientation is how a body is currently rotated relative to some set neutral orientation. So if we've got a bar sitting in space, I'd use X and Y to describe the position. I'd use that angle theta to describe the current orientation of the body. So by describing the position, usually the center of mass of the body, along with the current orientation, we can fully define the current location of the body. So without theta, we can have it sitting at any sort of angle, and it's not going to be fully defined in terms of its kind of complete location. So in 3D, if we move there, so in two-dimensional motion, a single angle is enough to define the orientation. We're going to have theta, we go kind of clockwise or counterclockwise from some zero angle. However, when we move to three-dimensional motion, we'll need to find 3 angles to fully define the orientation of an object. So it corresponds to the relative rotation of about each of the 3 axes. So if we're in 3D, we have X, Y, and Z rotations. And you kind of think about this in a plane. So we can roll, kind of move the wings up and down. So roll, pitch, kind of pitch the plane up and down, move the front of the plane up or down. And then yaw would be the third direction. So we can rotate about any 3 of these axes. And we need to define kind of each of these orientations to fully define the orientation in 3D. All right, so next up we have angular displacement. So the angular displacement of a body is simply the change in orientation between 2 points in time. So some delta theta in this case. So if we rotate so many degrees clockwise or so many degrees counterclockwise, that is our angular displacement. In 2D, we treat this as more or less a scalar value. So we've only got one angle. And so in 3D, though, we need to represent this as a vector quantity indicating the change in angle about each axis of rotation. So next up is angular velocity. So angular velocity is the change in orientation over the change in time, or more accurately, the rate of change of orientation over the rate of change of time at any given instant. So omega, this is Greek letter omega, is delta theta, or d theta dt. And over any finite period in time, the average angular velocity will be the change in orientation or angular displacement, that delta theta, over the change in time. So omega average is delta theta, delta t. So angular displacement over time between point 1 and point 2. All right, so just as with regular velocity, angular velocity is a vector quantity, meaning it has a magnitude and direction. So the angular velocity will lie along the axis of rotation. So think about the axis that the object is rotating about, and we're going to use the right-hand rule to determine direction. So the right-hand rule is as follows. So you're going to kind of put your thumb in the direction, or sorry, you're going to curl your fingers. So take your right hand, curl your fingers in the direction of the rotation, and you're going to stick your thumb out. So if you use your right hand, your thumb should be pointing along the axis of rotation, and the vector is specifically going in the direction that your thumb is pointing. So this is going to be used to determine the angular velocity vector that we use to represent this angular velocity. So if you think about something like this, this ceiling fan that we have here, if you imagine curling your fingers, use your right hand, curl your fingers in the direction that the blades are moving. And if that's the case, your thumb would be sticking straight down, which is the central axis that this whole thing is rotating about. All right, so finally we have angular acceleration. And so this is the rate of change of angular velocity over the rate of change of time. So alpha is what we use to represent the angular acceleration, and d omega dt, the rate of change of angular velocity, omega dt, is our angular acceleration, our definition of that. All right, so since angular velocity itself is the rate of change in orientation over time, the angular acceleration is also the double derivative of the change in orientation over the change in time. So d omega dt is d squared theta dt squared. So the derivative of the orientation over time. All right, so just as with angular displacement and with angular velocity, acceleration is a vector quantity, meaning it has a magnitude and direction. And again, the acceleration vector is going to lie along the axis of rotation. We're going to use the right-hand rule, just like we used to determine the direction of our angular velocity. So curl your fingers in the direction of the angular acceleration, kind of direction of motion, and stick your thumb out on your right hand. That is the direction of your angular acceleration vector. All right, that's all we have for today's video lecture. Thank you for watching, and I hope to see you